Hello and welcome to Math321. This is after we've done all the root finding stuff and we're moving towards interpolation. So I've been a bit slack updating these videos. For that I apologize, but here we go. So interpolation is the process whereby you're given some values of the function. A function, any function. So these values might be on the real line, and you might know what the function looks like, and you want to work out what the function, or estimate what the function might be in between the points where you know the function is. So in this particular case, the function might look something like this. That is a piecewise linear interpolation. Or maybe we want to make this smooth kind of thing, like a quadratic, or a quintic, or a polynomial. In which case the function might look something like this. In any case, uses for this kind of numerical technique involve estimates of differentials, differentials of the function, and also estimates for integration of the function. More generally, this is also while I'm going to be talking about interpolation, so that's where we assume that there's no error in our measurements of the function over the points that we've chosen on the real line. A small generalization of what you're going to see is related to least squares, regression techniques. Things that you might see in statistics, where you're trying to estimate a particular function by measuring some values of that function. And you'll see some things a little later on which are kind of related to that. But in any case, interpolation. So in order to derive our error results for interpolation, I'm going to start with Rolles' theorem. Which, as you'll see, will turn out to be quite important. So let f be a real valued function from the real line to the real line, so that fa equals fb equals 0. Right, and if f is first differentiable, and continuously so between a and b, then there exists some point c inside the open neighborhood, so it can't be equal to a or b, so that f dash c equals 0. Now if the function is constant, and so equal to 0 everywhere, you can choose a c, of course, in the interval which is not equal to a or b, and so that the derivative is equal to 0, so that's not a problem. The proof, if you've done a real analysis course, this follows from the fact that a and b is continuous, a and b is compact, and f is continuous. So we let f of x equal the min of fx for x inside ab. This x0 will definitely exist inside our interval ab because f is continuous. We let fx1 equal the maximum of fx equals. So of course, if the min and the max are equal to each other, then the function is just a straight line, and by the condition, it has to be equal to 0 everywhere, and so the result follows. Otherwise, of course, if it's not a straight line, then here's how the argument goes. Consider the limit as h goes to 0 from the positive direction of fx1 plus h minus fx over h. Now fx1 is the maximum, so this has to be less than or equal to 0. We take the limit as h goes to 0 from the negative direction of fx1 plus h minus fx over h, and that has to be bigger than or equal to 0 because h is negative in this case. So that will be positive, this will be negative. And that will be positive because, that will be, sorry, yes, slightly less. Have I got the signs the wrong way around? Hold on a second. No, everything's right. Important to check though. So this term here will be less than that term there because x1 is where the maximum occurs, so that's a negative value, and h is positive, so we have less than 0. Similarly, this the value on the top will be negative and the value on the bottom will be negative, so we have a positive value. And of course that implies that f dash at x1 is equal to 0. And you can derive the same thing for the minimum, so that gives the result. Now, for our purposes, Rolles' theorem is not quite good enough, and we need the generalized Rolles' theorem. Generalized Rolles' theorem is not a particularly great extension of what I've shown you, and it follows by an inductive argument. So we're going to take our function f, and we're going to assume that f is in n minus 1, sorry, Cn a, b. If there exists n plus 1 distinct points, x0 up to xn, inside our interval, so that fxi equals 0 for all I, 0 up to n, then again there exists a c inside the open interval, so that the nth derivative at c is equal to 0. The proof is reasonably easy. We do it by an inductive reasoning. N equals 1 is Rolles' theorem, so that's already been done. And assume true for n minus 1. So for all I equal to 0, and I'm taking n minus 1 now, we know that fxi equals 0 equals fxi plus 1, and that implies that there exists, and I'm going to call this a ci, inside the open interval, xi to xi plus 1, so that f dash of ci equals 0. Now f dash is an element of Cn minus 1 inside our open interval, and it vanishes on n minus 1 distinct points. So the inductive assumption implies that there exists some c inside the open interval, so that the nth minus 1 derivative of f dash is equal to 0 at c. And of course the nth minus 1 derivative of f dash is itself equal to the nth derivative of f, and that gives us the result. So that's Rolles' theorem and generalized Rolles' theorem. We'll need them for the error result for linear interpolation. So make sure you know these, or the proofs at least, and you can replicate them.